There is a question people ask me more than almost any other question about the universe, and on the surface it sounds perfectly reasonable. What happened before the Big Bang? I understand why people ask it. Every experience in your life has trained you to believe that everything must have a before. Before you entered a room, you were outside it. Before a building existed, there was an empty lot. Before you were born, your parents had lives, your grandparents had lives, and the world continued without you. Everything you know appears inside a sequence. One thing happens, then another thing happens, and the mind naturally assumes that the universe itself must follow the same pattern. But the deeper we look into cosmology, the more suspicious that question becomes. What if there was no before? What if the Big Bang was not an event that happened at a particular moment in an already existing timeline? What if the timeline itself begins there? When you imagine the beginning of the universe, you probably picture darkness. Maybe you imagine a black, empty space waiting in silence, and then suddenly there is an explosion. Light appears. Matter flies outward. Galaxies eventually form. That image feels intuitive. It is also almost certainly wrong. The Big Bang was not an explosion that occurred at one location inside empty space. It was not a cosmic bomb surrounded by darkness. Space itself was part of what was expanding. The event did not happen somewhere. It happened everywhere. And if space emerged with the universe, time may have emerged with it as well. So when you ask me what happened before the beginning of time, you may be combining words in a way that sounds meaningful while asking for something that physically cannot exist. It is similar to asking what is north of the North Pole. You can travel north from New York, you can travel north from London, you can travel north from almost anywhere on Earth. But when you reach the North Pole, every available direction leads south. There is no additional north beyond the point where north ends. The question is grammatically correct. The geometry rejects it. The same may be true of the word before when applied to the origin of the universe. Before is a relationship between two moments in time. If there is no time on the other side of the Big Bang, then the word loses its physical meaning. And I want you to notice how unsettling that is. The human brain was shaped to survive in a world of cause and effect. A sound in the bushes happens before an animal attacks. Clouds gather before rain begins. You throw a rock before the window breaks. Our minds are built to organize events into sequences because sequence helped our ancestors survive. But the universe is under no obligation to match the instincts of a primate brain. The laws governing the first instant of reality may not resemble anything you encounter in ordinary life. Cause and effect may behave differently. Time may not be fundamental. The distinction between past and future may not exist at the deepest level. And that is where cosmology becomes more than astronomy. It becomes an investigation into the architecture of reality itself. Now, saying that time may have begun with the Big Bang does not solve the mystery. It only changes the mystery. Because once I stop asking what came before, I must ask something even more difficult. Why did the universe begin in the state it did? Why was the early universe so organized? Why was it smooth enough to evolve into the cosmos we observe today? Why did it contain the particular laws, quantities, and relationships that eventually allowed stars, planets, chemistry, and life to emerge? When people hear the phrase Big Bang, they often imagine chaos. They imagine disorder in its most extreme form. But the early universe was not simply a random explosion. It possessed a remarkable degree of structure. Look in one direction through the universe and measure the ancient radiation left behind from its early history. Then look in the opposite direction. You find that the temperatures are almost identical. That may not sound surprising until you calculate what it means. Those distant regions appear to have been separated so quickly that under the simplest version of cosmic expansion, they should never have had time to exchange information. One side could not send a signal to the other. There was no opportunity for them to coordinate their temperatures, and yet they match with extraordinary precision. It is as though you entered two rooms separated by an enormous distance, discovered that both contained exactly the same temperature, and then learned that no heat had ever passed between them. Why? Why was the universe so uniform? Why was space so geometrically close to flat? Why are the galaxies distributed in patterns that grew from tiny fluctuations in an otherwise smooth cosmic background? These are not decorative details, they are clues. And one of the leading attempts to explain them is a concept called cosmic inflation. Inflation proposes that in an unimaginably brief fraction of a second, the universe expanded at an extraordinary rate. Not objects moving through space faster than light, but space itself stretching. A region smaller than an atom could have expanded to an enormous size almost instantly. If that happened, areas that appear causally disconnected today may once have been close enough to exchange energy and reach the same temperature. Then inflation stretched them across vast distances. This could explain why the universe looks so smooth on large scales. It could explain why space appears so close to flat. It could also explain the tiny irregularities that later became galaxies. Quantum fluctuations in the earliest universe may have been stretched by inflation until they reached astronomical scales. What began as microscopic variations could eventually become the seeds of galaxy clusters, stars, planets, and everything around us. Think about that. The largest structures in the cosmos may have originated as quantum fluctuations. The pattern of galaxies across billions of light years may be the amplified residue of microscopic uncertainty. You exist because the early universe was not perfectly smooth. If it had been completely uniform, matter might never have clumped together. Gravity would have had no denser regions to pull upon. Stars might never have ignited. Galaxies might never have formed. Too much disorder and stable structure may have been impossible. Too much order and nothing interesting may have happened. The universe seems to have begun in a state balanced between uniformity and variation. That balance is one of the deepest mysteries in cosmology. But inflation creates a new problem. Once inflation begins, does it stop everywhere? Maybe not. Some versions of the theory suggest that inflation ends in particular regions while continuing elsewhere. A region where inflation stops can become a universe like ours. Other regions may stop at different times and become other universes. This process could continue indefinitely. Our entire observable universe may be one bubble inside a much larger cosmic structure. Outside our bubble may be other bubbles, and outside those, more. An endless sea of expanding space-producing universes. This is the multiverse. I want to be careful here. The multiverse is not a fact in the same way that the expansion of the universe is a fact. It is a possible consequence of certain theories. It remains debated. We do not currently possess direct observational access to other universes. But the idea is scientifically motivated. It did not emerge merely because someone wanted to create an interesting science fiction story. It emerges from attempts to understand how inflation works and whether it naturally becomes eternal. If a multiverse exists, the implications are staggering. Different universes might possess different physical properties. The masses of particles could vary. The strengths of forces could vary. The number of spatial dimensions could vary. The amount of dark energy could vary. Some universes may collapse almost immediately. Some may expand too quickly for matter to form galaxies. Some may contain no stable atoms. Some may be empty. Some may be violent. Some may have laws so different that the word life becomes meaningless. And then there may be universes like ours, universes in which stars live long enough to manufacture heavy elements. Universes in which carbon chemistry becomes possible. Universes containing planets, oceans, cells, nervous systems, and minds. This leads directly to one of the most provocative questions in physics. Why do the laws of our universe seem so precisely arranged for complexity? Change the strength of gravity, and stars may behave differently. Change the properties of nuclear forces, and atoms may not form as they do. Change the amount of dark energy, and the universe may expand so rapidly that matter never gathers into galaxies. Change the masses of certain particles, and chemistry may become impossible. The universe appears to occupy a narrow range of conditions that allow life as we know it. Some people see this and immediately conclude that the universe was designed. They say the constants are too precise. The conditions are too convenient. The result is too extraordinary to be accidental. I understand the emotional force of that argument. But science cannot stop at emotional force. We have to ask whether there are other explanations. One possibility is that the values we observe are mathematically necessary. Perhaps a deeper theory will eventually reveal that the constants could not have been different. What now looks like fine-tuning may simply reflect our ignorance of a more fundamental law. Another possibility is chance. Perhaps there is only one universe, and its properties happen to allow life. Improbable events do occur. But without knowing the full space of possible universes, we cannot calculate the probability honestly. A third possibility is the multiverse. If there are an enormous number of universes with different properties, then it is not surprising that at least some allow observers to exist. And of course, any observer asking why the universe allows, observers must already live in a universe where observers are possible. This is called anthropic reasoning. It sounds obvious, almost circular, but it has real explanatory power. Imagine a person waking in a room filled with breathable air and asking why the room contains oxygen. The simplest immediate answer is that if it did not, the person would not be there to ask. That does not fully explain who built the room or how the oxygen arrived, but it explains why the observer necessarily finds conditions compatible with observation. In the same way, we should not be shocked to discover that the universe permits our existence. A universe that did not permit observers would contain nobody to be shocked by it. But anthropic reasoning can become dangerous when used lazily. It should not become a substitute for explanation. I still want to know why the laws have the values they do. I still want a deeper theory. I still want evidence. The fact that our existence filters what we can observe does not tell us the complete story. It simply warns us that observers are not neutral samples of all possible realities. Now let us return to the beginning. If time did not exist before the universe, can the universe emerge from nothing? The word nothing is one of the most abused words in cosmology. When a physicist speaks of nothing, people often imagine philosophical nothingness. No space, no time, no energy, no laws, no fields, no mathematics, no possibilities. Absolute non-existence. But the nothing of quantum physics is usually not that. A quantum vacuum is not empty in the ordinary sense. It contains fields, it contains rules, it permits fluctuations, it possesses structure. Particles can appear as temporary excitations in quantum fields. Energy can fluctuate within limits permitted by the uncertainty principle. Empty space can have physical properties. So when someone says the universe could arise from nothing through quantum processes, ask what they mean by nothing. Do they mean the absence of particles? The absence of classical space? The absence of matter? Or do they mean absolute nothingness? These are not the same. If quantum laws exist, then we do not have nothing. We have a framework. And then the question becomes, why that framework? Why those laws? Why mathematics? Why is there a structure capable of generating universes? Every answer seems to move the mystery one step deeper. That does not mean the investigation is pointless. It means reality may not offer a final explanation in the form human intuition expects. Perhaps the universe has no external cause. Perhaps causality itself is an internal feature of time. If causes must precede effects, and time begins with the universe, then demanding a prior cause may be another misuse of everyday reasoning. People often say everything must have a cause. But physics does not clearly support that statement in the absolute form. Quantum events are not always described by deterministic causes. We can calculate probabilities, but not necessarily identify a classical event that forced one particular outcome. Radioactive decay is an example. We can calculate the probability that an atom will decay during a period of time. We cannot always identify a hidden clock inside the atom that determines the precise moment. The universe may contain events that are lawful without being classically predetermined. So the origin of the universe might not resemble a machine being switched on by an external hand. It may be a quantum process, or it may be something for which the categories of cause and effect do not apply. There are models in which the beginning of the universe is not a sharp boundary. One famous proposal suggests that near the earliest moment, time behaves more like a spatial dimension. In ordinary life, time and space feel fundamentally different. You can move left or right, forward or backward in space, but you experience time in one direction. Yet, in general relativity, space and time are already joined into space-time. Under extreme conditions, the distinction may blur even further. Imagine the surface of Earth. It is finite, but it has no edge. You can travel around it without encountering a boundary where the surface suddenly stops. A model of the universe could behave similarly. The beginning might be rounded off geometrically. Time could gradually transform in a way that removes the need for an abrupt starting wall. The universe could be finite in its past while having no singular boundary. No moment at which one must say, here is nothing, and immediately after it, here is everything. Instead, the earliest region could be smooth. The question of what came before would disappear, not because we found an earlier event, but because the geometry contains no edge-demanding one. This is known as a no-boundary approach. It remains speculative, but it reveals how dramatically our understanding of a beginning can change when mathematics replaces intuition. To the human mind, a beginning must be a line. Mathematics allows a beginning to be a curve. And this is why I never trust intuition alone when dealing with the universe. Your intuition tells you Earth is stationary. It is not. Your intuition tells you the ground is flat. Globally, it is not. Your intuition tells you time passes identically for everyone. It does not. Your intuition tells you two particles cannot influence a shared quantum state across distance in the way experiments demonstrate. Yet they do. The history of science is the history of nature correcting human intuition. The origin of the universe may require the largest correction of all. There are also models in which the Big Bang was not the absolute beginning. Maybe our universe emerged from an earlier cosmic phase. Maybe there was a contraction before expansion. Maybe the Big Bang was a bounce. In these scenarios, the universe shrinks, reaches an extreme state, and then expands again. But a simple, bouncing universe faces challenges. Entropy tends to increase. Structures and energy distributions evolve. It is difficult to create endless, identical cycles without accumulating disorder. Still more sophisticated cyclic theories attempt to solve these problems. One possibility comes from ideas associated with string theory. String theory proposes that the fundamental ingredients of nature may not be point-like particles, but tiny vibrating strings. It also permits additional dimensions beyond the familiar three dimensions of space. Within some models, our observable universe could exist on a multi-dimensional structure, sometimes called a brane. Another brane could exist nearby in a higher dimensional space. The Big Bang might result from a collision between these structures. Two cosmic surfaces approach. They collide. The energy of that collision fills the universe with matter and radiation. Expansion begins. In this picture, the Big Bang is not creation from absolute nothing. It is a transition produced by a prior higher dimensional event. The universe may pass through repeated cycles of approach, collision, expansion, and return. Again, this is not established fact, but it is a serious attempt to connect cosmology with deeper physical theories. And it teaches an important lesson. The Big Bang may represent the beginning of the universe as we know it without being the beginning of all reality. Our equations currently describe the universe back to extremely early times. But at the most extreme conditions, general relativity and quantum mechanics no longer fit comfortably together. General relativity describes gravity and the large-scale structure of spacetime. Quantum mechanics describes particles and microscopic interactions. Both theories are extraordinarily successful. But near the supposed singularity of the Big Bang, we need both at once. and we do not yet possess a complete theory of quantum gravity. The singularity may not be a physical object. It may be a warning from the mathematics. When an equation produces infinity, nature may not be telling us that infinite density literally existed. It may be telling us that the theory has been pushed beyond its valid range. The singularity could be where our map ends, not where reality ends. Another fascinating cyclic idea proposes that the distant future of one universe can become mathematically equivalent to the beginning of another. To understand this, imagine the universe expanding for an inconceivably long time. Stars burn out, galaxies fade, black holes slowly evaporate, matter decays, depending on processes not yet confirmed. The universe becomes cold, dark, and increasingly empty. At first, this sounds like the opposite of a Big Bang. The Big Bang is hot, dense, and energetic. The distant future is cold, dilute, and quiet. How could one become the other? The key is scale. If the far future universe contains only massless particles, then those particles do not experience scale in the same way massive objects do. Without stable rulers, clocks, atoms, stars, or structures, the enormous universe may be mathematically reinterpreted. The infinitely expanded end of one cosmic era could be transformed into the compressed beginning of another. One universe ends, another begins, not through a bounce in ordinary time, but through a change in how geometry is described. This idea is sometimes called conformal cyclic cosmology. It imagines an endless sequence of cosmic ages. Each universe begins in a Big Bang-like state. Each expands, each fades, each becomes the seed of the next. The universe may not have one beginning. It may have infinitely many beginnings, and perhaps no ultimate beginning at all. Notice how far we have traveled from the original question. What happened before the Big Bang? At first, the answer seemed to be nothing, because time began there. Then inflation suggested a larger environment generating cosmic bubbles. Quantum cosmology suggested emergence without classical causation. No boundary models removed the sharp edge of time. Brain models suggested a collision in higher dimensions. Bouncing models suggested a previous contraction. Cyclic models suggested that the end of one universe becomes the beginning of another. Science does not give us one comforting story. It gives us competing models and asks reality to choose. That is how science works. We do not vote on which idea sounds most beautiful. We search for observational consequences. Could another cosmic bubble have collided with ours and left a pattern in the ancient radiation? Could gravitational waves from the earliest universe reveal inflation? Could specific features in the cosmic microwave background support one model over another? Could quantum gravity leave traces in the distribution of matter? Could the mathematics of a theory make predictions that no competing theory can reproduce? Without evidence, a theory remains a possibility. Elegance is not proof. Popularity is not proof. Authority is not proof. The universe decides. And the universe may not make the answer easy to obtain. There is a limit called the cosmic horizon. Light travels at a finite speed, and the universe has a finite age. We can observe only the region from which light has had time to reach us. There may be vastly more universe beyond what we can see. There may be an infinite amount. We cannot assume the observable universe is the entire universe any more than an ancient sailor could assume the visible horizon was the edge of Earth. Our telescopes show us a cosmic sphere centered on us, but we are not at a special physical center. Every observer sees a horizon around themselves. The boundary belongs to information, not geography. This means some answers may be hidden beyond our observational reach. Other universes, if they exist, may be causally disconnected from ours. Events before inflation, if that phrase has meaning, may have been erased by expansion. The earliest quantum state may leave only indirect clues. Science may encounter questions that are meaningful but permanently difficult to test. That possibility should humble us, but humility is not surrender. We build better instruments. We create sharper theories. We compare predictions. We look for inconsistencies. We keep asking, because the act of asking these questions has already transformed our understanding of reality. A few centuries ago, people did not know that galaxies existed beyond the Milky Way. They did not know the universe was expanding. They did not know atoms had nuclei. They did not know stars create elements. They did not know space could bend. They did not know time could slow. They did not know the universe had a measurable history. Now we map radiation emitted when the cosmos was only a small fraction of its present age. We measure light that traveled for billions of years. We detect gravitational waves from colliding black holes. We analyze the chemical composition of distant galaxies. We reconstruct the life of the universe from evidence written in light. That is one of the most astonishing achievements of the human mind. And it happened because people refused to accept that mystery should remain untouched. Some people worry that scientific explanation removes wonder. I find the opposite. If you tell me the universe was simply created in its present form, the story ends quickly. If you tell me space and time evolved, quantum fluctuations became galaxies, stars forged elements, planets assembled from stellar debris, chemistry became biology, and biology developed consciousness, the wonder multiplies at every level. Scientific explanation does not make the universe less mysterious. It reveals how much mystery was hiding beneath the surface. Consider your own body. The hydrogen in you emerged from the early universe. The carbon in your cells was manufactured inside stars. The oxygen you breathe was forged through stellar nuclear reactions. The iron in your blood was created in violent cosmic events. The atoms in your body existed before Earth. Some may have passed through multiple stars before becoming part of you. You are not merely living in the universe. For billions of years, the universe expanded without anyone we know of asking why. Stars formed and died. Galaxies collided. Planets orbited silently. Then, in one small region, around one ordinary star, living matter acquired curiosity. We began looking upward. We created myths, then measurements, then telescopes, then equations. We learned that the sky was not a ceiling. We learned that the stars were suns. We learned that the Milky Way was one galaxy among many. We learned that the universe had a past. Now we are trying to look toward the boundary of time itself. And perhaps we will never find a final answer. Every explanation may reveal a deeper layer. If inflation explains the early universe, what explains inflation? If quantum laws generate universes, why do quantum laws exist? If a multiverse explains fine-tuning, what governs the multiverse? If the universe cycles eternally, why does the cycle exist? If mathematics is fundamental, why does mathematics describe reality so effectively? At some point, explanation may reach a foundation that has no deeper explanation. Or perhaps the chain continues forever. The human mind wants a final floor beneath reality. Nature may offer no floor. That is unsettling, but it is also liberating. It means ignorance is not an embarrassment. Ignorance is the condition that makes discovery possible. The phrase, "I do not know," is not the end of science. It is the beginning of science. When I say I do not know whether the universe emerged from a quantum state, arose from a prior cosmic cycle, formed inside a multiverse, or began without a boundary, I am not confessing failure. I am identifying the frontier. And the frontier is where the excitement lives. Certainty is emotionally satisfying. Questions are intellectually productive. The history of knowledge advances because someone becomes uncomfortable with an answer everyone else accepts. So when you ask what existed before the universe, I will not give you a simple answer merely because simplicity feels good. I will tell you that the word before may not apply. I will tell you that time may have emerged with space. I will tell you that the Big Bang may not be a singular beginning. I will tell you that inflation may have produced many universes. I will tell you that quantum physics changes the meaning of nothing. I will tell you that mathematical models can remove the boundary of time. I will tell you that our universe may be one phase in an endless cosmic sequence. And then I will tell you the most important part. We do not yet know. But we are learning how to ask the question more intelligently. That is progress. The universe does not become less extraordinary when we admit uncertainty. It becomes more extraordinary because somewhere inside this vast reality, on a small planet orbiting one star among hundreds of billions, a species emerged with the ability to imagine what might lie beyond the beginning. We are fragile. We are temporary. We occupy almost no cosmic space. Our lives last almost no cosmic time. Yet our minds can reach backward across billions of years. We can reconstruct events that occurred before Earth existed. We can write equations describing black holes we have never visited. We can detect radiation emitted near the dawn of the cosmos. We can ask whether time has an edge. That is the true wonder. Not that the universe was designed specifically for us. Not that we occupy the center. Not that reality guarantees us a purpose. The wonder is that the universe became complex enough to produce beings capable of questioning it. We are stardust with curiosity. We are chemistry capable of memory. We are atoms capable of mathematics. We are a temporary arrangement of matter trying to understand the permanent laws that arranged it. And perhaps when we ask what happened before the Big Bang, the universe is not merely being observed. Perhaps through us, the universe is examining its own origin. Perhaps every telescope is an eye the cosmos built for itself. Every equation is a thought it learned to think. Every question is matter becoming aware of mystery. I do not know whether there was a first moment. I do not know whether there are other universes. I do not know whether reality began once, cycles forever, or exists beyond the categories of beginning and end. But I know this. For a brief moment in cosmic history, we are here. We can ask, we can explore, we can doubt, we can learn. And in a universe filled with silent stars, expanding darkness, and mysteries older than time, the fact that anything can ask why there is a universe at all may be the most astonishing fact of all.